Okay, so we're going to get started with problem 5 here from the homework. So it just shows the figure to the right, basic mass spring damper system. It's got that governing equation there. And then it says, so we want to sketch the time history of the steady state response under these 3 conditions. So we talked about this yesterday in class. So you've got the driving frequency is less than omega n, when it's greater than omega n, and when it's equal to omega n. So what do these 3 conditions mean? Like what do you know about the response just given these 3 at one of these 3 conditions?
I'm trying to relate back to yesterday, and I'm really not positive.
Okay, that's fine. So yesterday, so specifically, when we remember that when omega equals omega n, that's when you get the resonant frequency, right? So I'm gonna go ahead and draw a plot there. And so if we have, so I'll just go ahead and draw the input force first. Actually, is the input drawn on here? No, it's not. So we've got time out here, and let's see. So we've got time, and then just the amplitude of the steady state over here. Then basically, so let's see, this one, we're not really given any initial conditions, nor do we know what omega is, except for when, what omega or omega n is. So we're just sketching it. We don't have any amplitude here. But when we get a resonant frequency, so when omega equals omega n, is going to be, and I'll draw that in red here, it's going to be a very high amplitude sine wave, right? And that's at a frequency of omega n. And that's because you're getting resonance. So the question here doesn't ask for the input plot to be drawn, but it would be something like this. Oh, that's awful. Going at the same frequency. So these are the same spot, but with a lower amplitude. And then if your driving frequency is much greater than omega n, you're going to have some lower amplitude. It's going to be down here somewhere, and your driving frequency and your response frequency are the same. So it's a high frequency but a low output, but a low amplitude. So it looks something like this.
What is that one again?
This is omega much greater than omega n. I'm going to, I don't like that. So it's a low, like I said, low amplitude, high frequency. And then I'll label this one. So this is driving frequency equals omega n. And then the last one, so if you have a driving frequency much lower than omega n, you're also going to have a low amplitude. And it's going to be a very low frequency, so a very slow curve like that. And again, here, because we don't know exactly what omega is or our natural frequency of this system, we don't know specifically what the amplitudes are going to be. We just know that at the natural frequency, it's a high amplitude, and other frequencies, it's lower than that. Any questions on this one? I see we've got Ebony has joined. Welcome. Did you have any questions, Ebony? Okay. Perfect.
Just to
So let's go ahead.
Sorry.
Yes.
So just to clarify,
No
that purple one is whenever omega is less than Wn?
Yes, that's correct.
Okay, thank you.
Okay. So moving on to problem 8 here. So we have the data for our steady state response, and we need to determine what, sorry, one moment. Determine what zeta and omega n are. So we can see it's underdamped, we can see it's harmonically forced. We've got some equations of motion. So this first problem, it says write the steady state response y of t in terms of the constants b, and that's equal to the magnitude of the steady state response. Phi is our phase shift, etc. So what we're given here in the problem is that y(s) of t is equal to some blank sine of blank t plus phi. So given that, so we know that b is the amplitude of the response. So what does that mean for this first blank here? What's that equal to?
Is it 1?
So it's actually going to be equal to b. Whoops, why did... and that's because of this condition, this definition here of b. So that's just telling us that b is equal to the amplitude, and the coefficient in front of a sine is always going to be the amplitude. Does that make sense?
Yes. So we're not expected to put in numbers then?
No, we don't have numbers quite yet.
Okay, got it.
We can see here, so if you're, yeah, actually that is kind of confusing. The answer key has a B right there. You can see that the amplitude, and I think we'll get to this in a second. So our steady state is this red curve, and that has an amplitude of 0.8. So B is going to be equal to 0.8, and that comes down here in just a minute. So this second blank right here, what's that one going to be?
Omega?
That's right. This capital omega term. Why is that, Sarah Lynn?
Because that's our frequency, our natural frequency. Is it natural frequency?
So it's the driving frequency. So we can see right up here that's the frequency that we're driving the system at. And at steady state, your response is going to be going the same speed. It's going to have the same frequency as your input. So that's how we know that one. And then, oh, sorry. This was apparently also a blank. So that last term right there is phi, which is your phase offset. And that what that measures is the distance between peaks here, between your input and your response. Okay. So moving on, we've got this table here where it's asking us to fill in the value of these various parameters and then once the value and the units that the value is in. So Sarah Lynn, earlier you said 1 for the amplitude, and that is the amplitude of the input. As you can see right there, the blue dotted line is our input. That has an amplitude of 1. And as far as units, does it say somewhere? Does it tell us what our units are anywhere?
I'm not seeing it.
I don't see it either. So in that case, we usually assume standard units. So it's going to be a meter, which is what they have in the answer key, but that is probably just because it's standard. Also, you know that the magnitude for this system, that's going to be a measurement of length. So that's why we're going with the meter. Okay. The magnitude of the steady state response B. So what's that one going to be?
Is that 1.8?
Mm-hmm. That's right. So that one is 0.8, and you can just see on this plot here. So the steady state response, these two peaks right there are at 0.8 on the graph. You want to be careful because our steady state response here and here, or sorry, not our steady state, our response at that point, those it's not reaching that amplitude of 0.8. That's because we haven't reached steady state yet. We're still kind of have some interesting things going on. Would you like some more clarification? Is that clear about the difference between a steady state response and a transient response?
Yes. So basically, we just need to, if we're given a graph like that, we just need to see where it settles out in order to find that first coefficient.
Mm-hmm. That's exactly right. And that unit is also going to be meter. I guess that's already filled in for you. So I won't worry about that. And now we're going to look at the period of the steady state response. So we're going to measure from peak to peak on time. So from between 11 and the next peak is at 19. Again, working on the right side of the graph because the period might be a little different in the transient response. So 19 minus 11 is 8 seconds. And then the frequency of the forcing function. How are we going to find, how might we figure out that one? Because it's not necessarily given, but it's this value of omega that we're looking for. So how do we find that?
I'm really not sure.
That's okay. So we just figured out the period. So the period equals 8 seconds. And our function of the period being equal to 2 pi over omega still holds for the frequency that's observed. So we just need to solve for that. And we also know that the frequency of the input and the frequency of the steady state frequency of the response are the same. So we just solve. We have 8 seconds divided by 2 pi. Oh, sorry, that's not right. I'm skipping steps in my algebra. So we have omega t is equal to 2 pi. And so omega is equal to 2 pi over 8. And that equals pi over 4. And that's radians per second. And then the frequency of the forcing and the frequency of the steady state response are the same. So the frequency of the steady state response, which also has a period of 8 seconds, is pi over 4 radians per second. Now looking at the phase of the steady state response. So the phase is just the difference, like I said over here, is the difference between the peaks, and it's the lag from the response that the response has behind the force. And so that's measured, so we can see right here that's 1 second. They're asking for it in radians. So let's go find an equation that can help us with that. Do you happen to remember any equation that will help us relate seconds to radians in this case? That is okay. Let's see here, harmonic forcing. Oh yeah. Okay. So the steady state response, I'm looking on page 80. And we've got its equation 4 there, where it says that phi is equal to a tan 2. Has anyone ever used a tan 2 before?
Yes.
Okay. A tan 2 of -2 zeta omega over omega n, and then 1 minus omega over omega n squared. So we evaluate that. So zeta, we have, let's see here. So we know this. So that's our system 2 zeta omega n. Then let's see. Where gonna give us this stuff? Let's see. How might we find zeta and omega n given this data here? Well, so we can find omega n. And that's because on this plot here, so I'm looking again on page 80, you have the amplitude ratios of B over A. So we know our amplitude ratio of B over A is 0.8. And so this plot is giving us B over A versus omega over omega n. And so, is this the best plot that we have? So the idea being, you find your amplitude ratio on the y-axis, and then let's see. Sorry, excuse me just a second. Sorry, so continuing what I was saying there about the plots. So you have multiple plots there. So if you know what your zeta value is, then you can match up your amplitude ratio with an omega over omega n. And then that'll show you where you're on the plot to get your, and then you can find omega n. Because there's also phase angle versus omega over omega n. Okay, it's given multiple zetas. Sorry about this. Just trying to figure out how we might find out what our zeta is, because we can't see from the graph how much damping there is, right? Because we have a forced response. Just looking through the book here. Okay. I'm gonna go ahead and move on from this one. The phase angle, and that's also, we're trying to, like I also said earlier, trying to convert that 1 second to pi over 4 to radians, and the answer is negative pi over 4 radians. But I'm just missing this function here, the whatever conversion that is. That's okay. All right, I will try and send out a clarification on that one. So it's moving on to the next part. We have considered the phase and of the steady state response that y of t makes with the forcing function. So negative phase Does that mean that that the steady state of y, does it lead or lag the forcing function?
Does it lead?
Wouldn't it be?
So
I was
go ahead, Emily.
I was gonna say lag, but I don't
Why do you think it's lag?
know. Cause isn't it in the equation? There's already a negative sign in there, so it's gonna come out positive.
So this one actually does not have that. There is a positive sign right there, but you are right that negative phase means you're lagging, and that's because at time, so we'll say time t equals 10, we have a peak in the forcing function, and the associated peak in the response doesn't come until time t equals 11 here. And so, we do have a negative phase angle, and so we lag behind the forcing function. The response, by definition of it being a response, is always, we'll say always, going to have a negative phase, and that's because a positive phase would mean that you know what the forcing function is before it happens, which is not feasible. And so that means that y of the steady state is later than the forcing function. Is that clear? Does that make sense, Ebony and Sarah Lynn?
Could you say it again? Like you said, it lags because the position will be later in the.
Yeah, that's right. Yep. So we can talk about, so our forcing function is so our force is increasing, right? It's positive, it's going up. And then we don't see the response do the same motion until a second later. So we say that the response is lagging behind the input. Basically, you've got you're like pulling something along, is what the force is doing, and then you see on the other end of the spring is actually what we have. Like when you push with a force on this block, you don't see anything happen on this block for about a second, and that's your phase lag.
Okay. So the force pushing the system, it happens first, and then we don't see it actually, the system actually move until a little bit later.
Okay. That's exactly right.
All right, that's good. Just want to make sure.
Yeah. Yeah, for sure. And so Sarah Lynn, is that clear? You said lead at first. Are you convinced?
Yes, I think so.
Okay. All right. So then just the next question here, that means that positive phase, if it's not lag, it must be a lead. So it leads the forcing function, which means that the steady state is earlier, which is very rare in systems, and that's because you would see movement on this block before you actually pushed this block, which doesn't make a ton of sense. And so you very rarely see systems leading their input. So then a negative phase, if we're looking at the plot, which way is the response shifted relative to the input?
To the right?
That's correct. It is shifted to the right. And you can see that, I'm gonna go ahead and erase some of my marks here. You can see that that this peak shifted to the right is where this peak would be. And then positive phase is shifted to the left. Okay. Any more questions about lead, lag, phase shifts, etc.? Mostly like wrapping your head around the right vocabulary, but are there questions there? Okay. So the next question is, provide two algebraic equations that can be used to determine numerical values for zeta and omega n. Next, classify those two equations by picking the relevant qualifiers from the following list. Okay, so our two equations, we were looking at them earlier, they're on page 80. They're equations 4 of chapter 13. And so they are that our amplitude ratio, B over A, is equal to 1 over the square root of omega n over omega squared minus 1, that whole quantity squared, plus 2 zeta omega n over omega squared. This whole thing is under the square root. And then our phase is going to be equal to a tan 2 of negative 2 zeta omega n omega n squared minus omega squared. So sorry about the confusion there. So we actually can't know zeta until we can solve both of these equations. So you need to know your amplitude ratio and your phase. Oh, is that what it is? Yeah. Okay. I'm so sorry for my scattered brain here. So the reason the lag is negative pi over 4 radians is because one period is 2 pi radians. And so you can see that one period, so there's one, so basically it's a unit conversion. It's a ratio. You have 2 pi radians in your 8-second period. And then you convert that to 1 second. And then that's your phase angle. Is that right? Did I do that math right? But the equation is going to be um, 2 pi over t. Is equal to your phase. So that's where we get negative pi over 4. Apologize for that. Sorry. Questions? Points of clarification. Is that clear?
Yes.
Okay. Perfect. All right. So back to this part B, we provide two algebraic equations that can be used to determine numerical values for zeta and omega n. Okay, we've written them out here. Next, classify them. So a quick classifications. Are they uncoupled or coupled?
Coupled?
That's right. They are coupled. Are they linear or nonlinear?
Non-linear?
Yep, they are nonlinear. Homogeneous or inhomogeneous?
Inhomogeneous?
Inhomogeneous, thank you. And there we go. Yes. And then algebraic or differential?
Algebraic?
That is exactly right. Thank you very much. So there's no derivatives in here. So then we just have a process for how to solve them. There are many ways, many different ways you can go about solving them. The answer key literally says use MATLAB to solve two nonlinear algebraic equations. And then considering that phi equals a tan 2 of b comma a is the same as tangent of phi equals b over a. So that's a bit of a cleaner solve there. But any questions about that? Okay, I think we are about out of time. Are there any questions about anything we've been over? Or if you've had the chance to look at the homework that's due next Wednesday, any questions about any of that or anything that was covered in lecture yesterday?
I think I'm good. I haven't really had
Okay,
time to look at the homework quite yet, so well.
that is fair. Mac, did you have any questions? That's how you came in here.
I appreciate it.
Okay, perfect. I'm gonna go ahead and stop sharing.